Hey everyone, welcome to the set of problems on the pigeonhole principle. Okay, there's some problems of very varying levels of difficulty in here, so try them out and then come back and have a look at the solutions if you want to. Okay, so our first problem is just a simple application of the principle. It says that we need to have two people in the room whose first names start with the same letter. I'm going to use the 26 English letters. You can use whatever letters you want. But since there's only 26 English letters, if we have 27 people in the room, then by the pigeonhole principle, we have 27 people, and the people are the pigeons, with only 26 letters, and the letters of the first names are the pigeonholes, so there must be at least two pigeons in one pigeonhole. There must be at least two people whose names start with the same letter. Our second problem here is much the same as the first problem, but in this case we're going to have way more pigeonholes, because this time we need their first and their last names to start with the same letter. Okay, so every possible combination of first and last name, first letter of the first name, first letter of the last name, every single one of those combinations is going to be a different pigeonhole. So how many combinations are there? Well, or maybe I should say permutations. There's 26 possibilities for the first name, 26 possibilities for the last name. That's going to give us 26 times 26 equals 676 pigeonholes. Okay, so if we have 677, then by the pigeonhole principle, right, we're guaranteed to have at least two pigeons in the same hole, or at least two people who share the first letter of their first name and the first letter of their last name. In problem 3, we're looking at a party that has some number of people. Let's call that n. And some of those people are shaking each other's hands, and some of those people are not. Okay, and we have to work out how we can show that at least two people shake the same number of hands. Okay, so we're using the pigeonhole principle, so we're expecting, well, okay, so our pigeons are going to be the number of people at the party, and probably our pigeonholes are going to be how many possible handshakes each person should have. So let's try and test that. So let's try and, well, we know there's n people, but how many hands can each person shake? Well, they could shake no hands all the way up to n minus 1 hands. Okay, but unfortunately in this range there are n numbers. So the pigeonhole principle does not work in this case because we have n pigeons and n pigeonholes. So we're going to have to break it down a little bit more, simplify this by breaking it into two cases. So the first case that I'm going to look at, okay, is where there is someone who shakes no one's hand. Okay, so in this special case where there is someone at the party who shakes nobody else's hand, someone who's not very friendly or who's socially isolating or something like that, in this case, well, what does that exclude? Well, it excludes the possibility that there's someone who shakes everybody's hand. There can't be someone who shakes everyone's hand. Why is that? Well, that's because they would have to shake the person's hand who shakes no one's hand, and that's a contradiction. Okay, so in this case, the possible range of hands that someone could shake is 0, because we know there's a person that does 0, up to n minus 2, because we know no one shakes n minus 1 hands, because that would be shaking everyone's hands. Okay, so given that, we say by the pigeonhole principle, we have, well, this is n minus 1 possibilities. And we have, so that's n minus 1 pigeons, and we have n people at the party, which is n minus 1 pigeonholes and n pigeons. I'm sorry. Okay, so now let's look at the second case, and it's just the other case, right? Where there's no one who shakes no one's hand. Okay, so in case 2, we have this possible range of hands that someone can shake. Well, we can't have 0, right? but we can have n minus 1. Someone could shake everyone's hand. So again, there's going to be n minus 1 pigeons, n minus 1 pigeonholes, and of course we have the n people out of the n pigeon. So by the pigeonhole principle, we can conclude that two people are going to shake the same number of hands. Okay, so we broke it down into 2 cases, and those 2 cases, they cover every possibility. Okay, so in this super cool problem that we have here, we're considering polyhedra, right? We're considering like 3D polygons like a cube or a tetrahedron or something like that, and we're saying, we're claiming that every single one must have at least 2 faces with the same number of edges. Okay, so what I'm going to do, since the pigeonhole principle tends to be about, maximum number of things, I'm going to consider that face of a given polyhedron like this one, for example. Okay, so there's like one side of a polyhedron. Alright, so I'm going to consider the face that has the maximum number of edges. So perhaps in this polyhedron we can't see the rest of it, but perhaps this face has the maximum number of edges. Okay, and 4 edges. But let's let in our general one, in any polyhedron we have, let n be, n is going to be the number of edges on the face with the most edges. Okay, great. So in this case here, n equals 4. Now, if n equals 4, what can we guarantee about the number of faces? Well, every one of those edges on this face has to be connected to some other face. Like, there's going to be a face here, and a face here, and a face here. And we can see there is a face here, this triangular face, right? So we can guarantee there's going to be at least n other faces. But we also have this face here, right? So if we have a face that has n edges, then, well, there's going to be at least n plus 1 faces. Right? So the number of edges that we can have, because n is the maximum number, well, the minimum is going to be like 3 or whatever, because you can't have a face with only 2 edges. And the maximum is going to be at n. Okay, so we're going to get so there's going to be like n minus 2 possibilities for the number of edges. But here's the thing, we have n faces. So if the possible number of edges is n minus 2, and that's the number of pigeonholes, and our pigeons are the number of faces, which is at least, what did we say? Well, it's at least n plus 1, right? There's at least n plus 1 faces. Then we have n plus 1 pigeons in n minus 2 pigeonholes, and so easily we're going to have at least 2, which have the same number of edges. We want to show that among any 4 integers we can find 2 such that their difference is divisible by 3. Okay, so we're considering the differences of integers of any 4 integers. Okay, so let's call those a, b, c, and d as I've written here. Right? And so we want our 4 integers to somehow be pigeons in 3 pigeonholes. So what can we say about integers where what property about them can be the same such that it means their difference is going to be divisible by 3? Well, if we know modular arithmetic, this is really easy, right? But if we don't know about that, well, how are we going to work this out? Well, let's see, when is the difference of 2 integers divisible by 3? We could look at some examples. We might notice, well, of course, the difference of 9 and 6, well, they're both divisible by 3, and that is going to be divisible by 3 as well. Okay, what about another example would be the difference of 10 and 7. That's also divisible by 3. So what's special about 10 and 7? What is the same about them that means that their difference is going to be divisible by 3? Well, what you might notice is that their own remainders when divided by 3 are both 1. Okay? So 10 divided by 3 is going to give 3, remainder 1. and 7 divided by 3 is going to give 2 remainder 1. Okay, so we can consider the remainders of numbers when divided by 3. And is it true that if two numbers have the same remainder when divided by 3, that their difference is divisible by 3? Well, let's check that out. Let's test that claim. We can prove it. So if the first number, we can write it as 3 if its remainder is R1 when we divide it by 3, we can write it as 3 times some number, I'll call it x, plus R1. Hopefully you can see why we can do that, right? This number here, when divided by 3, gives x remainder R1. And so we're also subtracting another number, which is going to be the same. This one's going to be 3y, and it has the same remainder, okay, plus R1. Okay, well, so here what we're going to get is the two R1s are going to cancel out. And then we're going to get 3x minus 3y, which gives us 3x minus y. Okay, and you can see this is clearly divisible by 3 because it's a multiple of 3. X minus y is going to be an integer because x and y are integers. Great, so now we know that if two numbers have the same remainder when divided by 3, their difference is going to be divisible by 3. What are the possible remainders when divided by 3? Well, there's 0, 1, and 2. Okay, so there's 3 possibilities. There's 3 pigeonholes, but we have 4 pigeons. So by the pigeonhole principle, we can guarantee that at least 2 of them are going to have the same remainder when divided by 3, so their difference is going to be divisible by 3. Okay, so this is a pretty tricky problem. We're asked to show that in any ordered list of 10 not necessarily distinct integers, for example, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or that would be a different list from 1, 3, 2, 4, 5, 6, 7, 8, 9, 10. Those would be 2 different lists. We're asked to show that there is some smaller ordered list inside of it. So for example, in the first example from before, we could have 3, 4, 5, 6 would be some smaller ordered list. And we want to show that the sum of the numbers in that list is going to be divisible by 10 for some ordered list in there. Okay, so because we plan to use the pigeonhole principle, we want to somehow kind of find 10 or 11 objects to be our pigeons or our pigeonholes in here, right? So the ones I'm going to consider is if we let each of our integers in our list from from all of the 10 integers in our list be a sub 1, a sub 2, a sub 3, up to a sub 10. Okay. Now, I want to consider the subsums, which are, the first one is S1. So these are sums of sublists, right? S2 is going to be A1 plus A2. S3 is going to be A1 plus A2 plus A3. So hopefully you can see this pattern. I'm just making up some names for sums of different lists that are inside of here. Okay, and I'm just picking 10 lists. There's heaps of lists in here, but I'm just picking 10 that I've specifically chosen, and we know that S10 is equal to A1 plus A2 plus A3 plus, and then all the way up to A10. Great. So these are some important sublists that we're going to consider. And so these sublists are going to be 10 different integers, right? And we're going to use really similar logic than we did in question 5. So I'm not going to reprove this fact, but we said that if two numbers, or in this case, well, if two numbers have the same remainder when divided by 10, okay, then their difference is going to be divisible by 10. So the difference of any two of these, for example, like S5 minus S3, well, that's going to be A1 plus A2 plus A3 plus A4 plus A5 minus A1 plus A2 plus A3, which is just going to be equal to A4 plus A5, right? So every difference between any two of these S sub and then a number is going to be the sum of some other list, like for example this one. Okay, so what we're saying is that we have all these numbers S1 up to S10, and so just like before, we can say, okay, well, we can find if we had 11 sums of numbers, we could use the exact same logic as before and say, okay, well, the difference between any two sums must be divisible by 10. Right? Between two sums in there must be divisible by 10. But in this case, we can't do that because we have only 10 sums. So we can't guarantee by the pigeonhole principle that there's going to be at least two that have the same remainder when divided by 10, so that their difference, which would be some other sum, would be divisible by 10. But in fact, we can just consider, imagine if that were the case. Imagine if we did have that problem that all of them had a different remainder when divided by 10. Each of S1, S2, S3, S4 all had different remainders, so the difference between no two of them was divisible by 10. But if that were the case, well, they all have different remainders, so one of them has to have a remainder of 0. When divided by 10, which means that one of them has to be divisible by 10. So essentially we have two cases. We have the case where S1, S2, S3, all the way up to S10 all have a different remainder when divided by 10. Well, in that case, one of them is divisible by 10 and we're done. If that is not the case, then we know that at least two of them have the same remainder when divided by 10, and so then we can find the difference of those two, which will give us some other sum, and that will be divisible by 10. So in both cases, we are done. In problem 7, we're given 10 integers chosen at random. They could be the same, they could be different. It doesn't matter. They're chosen from 1 to 100, okay, inclusive of both 1 and 100. And we need to show that we can find two subsets of these 10 integers with no common integers in the subset. So they're called disjoint. What that means is that, for example, if we chose the numbers 1 through 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then two subsets we could pick would be 1, 2, and 3, and 4, 5, and 6, right? That's breaking it into two subsets that have no common integers in them. Okay, and we can find that we're trying to prove that we must be able to find that two of these subsets have the same sum. No matter what integers we prove. No matter what integers are chosen. Okay, so what we're going to do in order to solve this is to consider an easier problem. What if they could have common integers? Okay, so let's suppose that they can have common integers in them, in the subsets. Well, how many possible subsets are there going to be? Right? Well, if we have 10 integers, and each of those, in each subset that we could pick, in every possible subset that we could pick, well, we could either pick each integer or we couldn't. So when we look at the first integer, well, we have two possibilities. In the second integer, we have two possibilities. So we're going to times 2 together by itself 10 times. And so for 10 integers, there's 2 to the 10 is equal to 1024 possible subsets of 10 integers. Okay, so there's a whole bunch of possible subsets. Now, those subsets, well, they can be our pigeons, right? Just if the number of possible sums were our pigeonholes. Well, what's the largest possible sum that you could have of 10 integers from 1 to 100? Well, it would be if we had all 10 being 100, which would be 10 times 100 is equal to 1000. Okay, so the largest sum equals 1000. So the number of possible sums is, well, it's anywhere between 0 and 1000, but we have 1024 subsets. So by pigeonhole principle, we can guarantee that at least two subsets are going to have the same sum. Well, that was good and all, but it doesn't work for every case because we said we can't have any common integers. And a lot of these 1024, a lot of them do have common integers. So that's problematic. But here's the big trick, right? Because what we can do is for any two, let's imagine that two subsets which have common integers have the same sum. Right? Let's imagine they have the same sum. So for example, it could be like 4 plus 5 plus 6 is equal to, well, let's say, 3 plus 6 plus 6. Okay, I think that's true. Now, these are two subsets, 4, 5, and 6, and 3, 6, and 6, from some set of 10 numbers. Well, they have common integers in them, so what we're going to do here is we're going to just take the common integers out of both subsets, right? Well, 6 is common to both, so I'm going to take 1 6 from each side. And of course, that's like me subtracting 6 from both sides, so it's still going to be true. So if we can find, so now we have two subsets which are disjoint. They have no common integers, 4, 5, and 3, 6. Those are two subsets that have no common integers but still have the same sum. So if we can find any two subsets which have the same sum, we can just reduce those to find two subsets that have the same integers in them that have the same sum. So then we're done by this. Okay, so for our final problem, we are picking another 51 integers between 1 and 100 inclusive, and we need to show that it is possible to find A and B such that A is a multiple of B or B is divisible by A. So we want to find some number and its factor in any set of 51 integers from 1 to 100, right? So we want to use the pigeonhole principle, so we're going to need to somehow get, like, how are we going to get, why is 51 important here? How could we break this up into 51 groups? That's an interesting question, okay, or 50 groups in this case, because 51 is probably going to be our pigeons, and 50 is probably going to be our pigeonholes. Well, how about we consider all the odd numbers? There's going to be 50 odd numbers from 1 to 100 inclusive, from 1, 3, 5, etc., all the way up to 99. Okay, so we have, in here, we have about, well, exactly 50 odd numbers. Now let's create a whole bunch of groups, right? These groups can be our pigeonholes, and each group is one odd number. Okay, and all of that number times powers of 2. So let me show you what I mean, because that's a hard thing for me to say in words. But so here we have 1 is going to go in this box, right? It's already there at the top. And now we're going to have 1 times 2, and then 1 times 2 times 2, and then 1 times 2 times 2 times 2, okay, etc. So this box is going to have all the powers of 2 up to 100. Okay, so the biggest one will be 64 in that box. Okay, now this one is going to have 3 times all the powers of 2. So it's going to have 3, and then it's going to have 3 times 2, and it's going to have 3 times 2 times 2, and 3 times 2 times 2 times 2. Okay, so it's going to have 3 times all the powers of 2 up to 100. And this one is going to have 5 times all the powers of 2. And this one, well, we're going to have all the other ones in between here in our 50 different pigeonholes that we have, but this final one is just going to have 99. Okay, well, it's already there. Right? So can you see how all of these different pigeonholes are necessarily going to have all the numbers from 1 to 100? Well, that's because if we think about prime factorizations, every even number, every even number is either just a power of 2 over here, or it can be written as some power of 2 times some odd number, which is some odd primes which are in its prime factorization. Okay, so given that, we have every possible odd number along the top and every possible even number lower in the columns. Okay, so every single number is here in one of these pigeonholes, and we have 51 numbers. Right? We're picking 51 numbers that we're going to slot into 50 pigeonholes. Okay? Into each of these 50 pigeonholes. But here's the thing. If there's 2 numbers in the same pigeonhole, well, every number in a pigeonhole is either a factor of or a multiple of another one. Right? So for example, 2 and 4, 2 times 4 is going to be a multiple of 2, or 8 is going to be a multiple of 1 if you're in this one, or in this case, 24 is always going to be a multiple of 3. So what we can say is, because we have 51 pigeons in 50 pigeonholes, there's going to be 2 numbers in the same pigeonhole, and those 2 numbers are going to be, well, one of them is going to be a factor of the other. One of them is going to be a multiple of the other, and that finishes the proof.